Okay, all right, so let's go ahead and start with this then. Okay, so first of all, to look at what the meaning of an improper integral is at this point in time, every integral you've done has had two characteristics to it. Okay, you've always integrated from, let's just use a simple example like you're integrating from 1 to 3 of dx. Okay, what you've done is the limits of integration, they are on a boundary, they are bounded. And what we mean by that is 1 to 3, there's an interval. That's a defined interval. It's not like 1 to infinity, okay? It's bounded. There's a definitive starting point, there's a definitive end point. And then this thing, we call this thing the integrand, that's what you're integrating, it's also bounded, okay? So what you've done is you've never done an integral where you've tried to find the area of a curve where there was like a vertical asymptote, okay? And like that area was unbounded, okay, or something. So everything has always been a boundary. In other words, everything that you've seen, like if you've looked at an area under a curve, like something like this, you've always just been looking at something that is totally bounded. In other words, just think of, you could draw a circle around it, okay? If you have an asymptote or something like that, you can't draw a circle around it, okay? That's a simple way to look at that. So when you're doing an improper integral, one of those two conditions doesn't hold. Either the limits of integration are not bounded, meaning something like negative infinity to infinity, or the integrand might have an asymptote, so it's not bounded. So those are the two conditions that you get into. Okay, and we're going to basically just look at those two things, and you got to go back to doing lots of limits in this section. So basically, this is what an improper integral is. The interval of integration is infinite. An example of that would be you're integrating from 0 to infinity. The other possibilities would be negative infinity to infinity, or you might be doing just negative infinity to 0 or something else. So you got an infinity in there somewhere, so that's not bounded. Okay, and then the integrand, the other case, which is the second part of this, is the integrand's unbounded. Okay, an example of that might be something like, well, the problem I'm getting ready to do, 1 over x squared. Okay, if you graph 1 over x squared, first of all, where is 1 over x squared undefined? At 0. So what you'd find is you have a vertical asymptote at 0, so you're not bounded. And that's the graph that I have down below like that I just pulled up on my calculator. So it's not bounded, okay? Because if you were trying to find the area under the curve here, doesn't that just keep going on forever and ever and ever? Okay, so you couldn't draw a circle around that, so it's unbounded. So those are the two features that you have on an improper integral, is something's unbounded, either the limits or the integrand. Does that make sense? Okay, those are the two cases that we explore, okay? So now we're going to go through and do several of these things. And the idea with this one is, now your handout may have had a typo. Does your handout say 0 to infinity? It needs to say 1 to infinity. I caught that when I was looking over that. I typed that wrong. There's a reason for that, okay? So it's just, I want to look at 1 to infinity, okay? Not 0 to infinity. Because what we're going to look at is we're going to look at case 1 is the interval of integration is unbounded. Okay, that's infinite. Okay, so you're going from 1 to infinity. But the integrand is bounded, and this is supposed to say from 1 to infinity. We're not going to look at where both of those things exist. We're just looking at one is unbounded, the other one's bounded. Okay, we're kind of categorizing it like that. Okay. So what we're going to do is we're going to go ahead and see if we can just figure this out, kind of analytically, okay, just on this first one like this. So the idea with this one is going to be, okay, you're going to find the area under the curve from 1 to infinity. So just imagine in your mind, you got that area right there. Now that's going to go on forever, right? It's never going to hit 0 because you have a horizontal asymptote, okay? The idea is x goes to infinity, then the function just goes to 0. So you're always going to have a little area under there, aren't you? Although it's going to get tinier and tinier and tinier and tinier as you go further out there then, okay? So this is always kind of a heavy idea to students when they're taking calculus is it possible that that area could have a finite answer? Yes, it is, okay? It does work out that way, but sometimes it doesn't, okay? So we're going to find out on this problem that it will have a finite answer if we go about doing this the right way, okay? So here's what I want you to do first of all. We're going to cheat, sort of, okay? Sort of cheat. This is the way mathematicians would figure this out. Instead of saying 1 to infinity, we're going to say 1 to b. Okay, our textbook tends to use a look like b. I see that a lot in textbooks. So we're going to do the integral of 1 to b of 1 over x squared dx. Okay, just forget about the infinity for now. We'll deal with that later. So we're going to go ahead and integrate this. This is a real simple integral. So we're going to go 1 to b, write that as x to the negative 2 dx like that. Okay, now what's that integral going to be then? Let's see, that's x to the negative 1 over negative 1, and then you're going to evaluate that from 1 to b, like that. Add 1 to the exponent, divide. That's power rule. So I'm going to write this as negative 1 over x from 1 to b like that. Okay? Everybody okay so far? Okay, that's a basic power rule integral. So let's see, when we do this, we're going to have negative 1 over b minus, and then you'll have minus negative 1. You can do it this way if you want to, or you can just factor the negative out. Negative 1 over 1 like that. Okay, so what I'm doing is just evaluating the upper limit b, and then I'm doing that. Okay, so let's simplify that. So that's negative 1 over b plus 1. Okay, so that's the antiderivative, and that's evaluated from 1 to b, with b just being an arbitrary number. Okay, now what we're going to do is we're going to do the limit of this, because we're interested in what's happening as b goes to 0. So it's not really cheating, it's just kind of a way to look at this. So we're going to take the limit as b goes to infinity of this result, negative 1 over b plus 1. Okay, like that. Now, Calc 1, you learned how to do some things with, you learned how to do some integrals with infinity, didn't you? Okay, so let's see if we know this, because you're going to do this throughout the section, as you're going to do limits like crazy. Okay, now you can do this all in your head. I'm going to write down technically what I'm doing, as I'm using limit laws. I won't always write every little step out, but that's what you're technically doing. One of the things you learn in Calc 1 is the limit of a sum is the sum of the limits. Okay, now we haven't done any limits like this semester, so do you know what that limit is right there? That's 0, exactly. The idea, the central idea is no matter what's in the numerator, if you just have a constant in the numerator and you have something infinitely big there, where does that go? It goes to 0. I mean, the numerator could be a quadrillion, but if you divide that by something that's infinitely bigger, it's going to approach 0, right? So that goes to 0, okay? And then what's the limit of a constant? It's itself, it's 1, okay? So that means the area under that curve is a finite answer. It's beautiful too, it's 1. How elegant is that? Man, I think that's elegant. What do you think? Yeah, it's kind of cool, okay? That's the idea of calculus. When I was a student, the idea that you can have a finite answer out of something that's unbounded like that, but you can't. That's the power of the limit. So that is the precise area under that curve, okay? All right, that's pretty, you got to wrap your mind around that one a little bit, but the math works out beautifully, doesn't it? Okay, so that's a good starting example. Is there any question about the idea? So what the key was I just changed that infinity to b, and then at the end I do a limit. Okay, that's what you're going to do on this style of an improper integral, okay? Now on this next page, I gave you this diagram. This is a fairly nice diagram that's in the book, and these are the different cases that we're going to look at. And again, what we're looking at on this is, what we're looking at right now is the limits of integration are unbounded. So we're going, notice that you have an infinity in the limits of your integration. That's case 1, okay? The function is going to be bounded though. So if you're doing the limit as from a to infinity, you're going to change this like this. The idea is you're starting at a and then you're going forever like that. So what you do is you just do this sneaky trick, Okay, instead of calling that infinity, you call it b, and then at the very end of the problem, what do? You do the limit as b goes to infinity. So you just replace that infinity with b, then you do that limit. Okay, that's what I just got through doing. Okay, if you had a limit like this, and I'll do one of each case. If you're doing negative infinity to b, that means that you're way over here, and then you're coming up to b like this. What we're doing on this basically is notice that we're doing the limit as a goes to negative infinity. Okay, so we're starting with the lower limit there, and we're going up to b. So it's the same idea. You just use a variable to use for infinity, then you do the limit. Okay, does that make sense? Okay, and it doesn't matter how you, what you use for that variable. That's just kind of your choice. I usually use b or c or something like that. Okay, then the last one. And then this is the one you got to be kind of careful about. If you're doing an improper integral from negative infinity to infinity, you have to break it up into two different integrals. So what you're really doing is you're saying, okay, we're going to integrate from a to c, and that's really going from negative infinity until we get to some point. That point can be several different things. Okay, so you're going to do that integral from there to there, and then you're going to do that integral from there from c to infinity like that. And the thing on that is you got to, when you're breaking this up into an interval, the reason you do this is because you're only going to be able to do a limit where one of these things is a specific constant and the other thing goes to infinity. You're not going to be able to do a limit with both of those things one of them going to infinity and one to positive infinity. So you got to break it up into the limit that's going to negative infinity and the one that's going to infinity. Okay, so you have to use two integrals in that case, yes. Depends on the situation, and we'll look at that because there's going to be times when maybe there's something going on, like there's an asymptote or something somewhere. Like that 1 over x squared that we did. Like if you look at this example that we did here previously, okay, if you were going to do that limit from negative infinity to infinity, it'd be a little bit different idea. You would have to do this limit. Okay, then you'd have to do that limit. You have to break it up into two limits. 0 is a good choice because there's an asymptote there, but there's functions that could have asymptotes other places too. Okay, so it kind of depends on the situation. Okay, and let's see. Yeah, this is kind of what this is saying. This is kind of important, is you can't do this like this. Well, that's the reason why you have to break that up into two limits. You can't just say the limit of infinity and then make that a negative b and a b. It doesn't work well that way. So you got to use two integrals when you do that. Okay, so we're going to crunch out several examples of this. Let's see, your handout, did I have the graphs on your handout? I tried to just do these on the calculator because I think visually those things always help a little bit. So what I did in this situation here is I just graphed this on my calculator. So this is like going to 0, and I know that's going up to 1. The reason I know that's going up to 1 is because if you do e to the negative 2 times 0, you get e to the 0, and that's equal to 1. So you do have a y-intercept right there. That's a definitive point. That's 0, 1, okay? So that's where that comes from, and we're going to be doing the integral from 0 to infinity. So we have that. Okay, so the situation on this is the limits of integration are unbounded. Okay, the function, we call that the integrand, is bounded. Let's make sure everybody knows what I mean by that. The limits, if the limits are unbounded, it just means one of those limits has an infinity. Okay, that's what we're going to focus on right now. And then the fact that that integrand is bounded, what that means is if we're going from 0 to infinity, okay, like that, this area under the curve right there has boundaries to it from here to someplace else. Okay, not to infinity, but just from 0 to some other point on there. Yes? Yes, yeah, we'll get to that case. That's the second part of that, is you may be integrating around a vertical asymptote. Right, exactly, okay? All right, so what we're going to do with this one then is you're finding this area under the curve there, and you know sometimes it'll give you a finite answer, sometimes it won't. We'll see that. Okay. So what we're going to do is we're going to go ahead and just set this up like this. Like I say, we cheat kind of. So we go ahead and just change this to 0 to b, and then we're going to do the integral of e to the negative 2x times dx, and then what are you going to do? You're going to take the limit as b goes to infinity, right? Okay. That's how you want to start these problems off, is you change it into a limit and you substitute that infinity with some variable. So I'll just keep using b like that. So that's what you work out as you work out that limit, okay? So the first thing to do is, you know, the first half of this problem is you need to just focus on doing that integration, okay? So yeah, you're going to work out a ton of integrals in this section. So some of these things you'll be able to do with all the different strategies we've learned. So we're going to have limit as b goes to infinity. Okay, what's the antiderivative of that? Okay, it's 1 over k e to the kx. It's just itself, like this. It's itself, but then you got to do 1 over that constant like that, right? Okay, that's a formula we learned. You could do U-Substitution if you don't remember that, but it's kind of helpful on exponentials to remember that. Then we're going to evaluate that from 0 to b. Okay, so we got to focus on the integral first of all, okay? Now I'm just going to keep drawing this limit just kind of so I don't forget about that. So now we have the limit as b goes to infinity. Then we got a negative 1/2, and that's a constant. You could even pull that negative 1/2 out of the limit. You can pull constants out of a limit if you want to. I'm just going to do it like this. So I'm going to have plug in the upper limit. So we'll have e to the negative 2b minus e to the negative 2 times 0 like that. Okay, so that's a basic integral. That's an integral formula. Now we're evaluating it. Okay, all right, let's push on and see what we get here. So now we have the limit as b goes to infinity of negative 1/2. Now I'm going to write that as 1 over e to the 2b. Okay, like that. That's a good way to write that when you're doing your limit. And then this next one's going to be e to the 0 like that then. Okay, and I forgot my 1/2 there, so I got to be careful on that. What I would probably suggest is just do it this way. Okay, if you have a limit of a constant times something, you can pull that out. Okay, you can do that. That's a limit law. So I'm just going to pull that thing out. Then I'm going to have 1 over e to the 2b minus e to the 0 like that. Okay, does that make sense? That's one of the limit laws. So if that constant is times everything, just pull it out. Okay, so let's see what we have now. So now we're going to have negative 1/2, and we're going to have the limit as b goes to 0, or b goes to infinity, of 1 over e to the 2b minus 1 like that. Okay, now we're ready to do our limit. Now a lot of these limits you'll be able to do in your head. Okay, as I'm teaching this, I'm going to kind of carefully show you what I'm doing. So really what I'm going to do is I'm going to take negative 1/2, I'm going to do the limit as b approaches infinity of 1 over e to the 2b minus the limit, and I'm going to kind of quit writing this step here in a minute, just kind of give you the idea on the first couple of examples. So the idea is the limit law is the limit of a difference is the difference of the limits, like that, okay? All right, now it's pretty simple. You'll see this over and over again. What do you think that limit is? 0, okay? You got to understand that if you have 1 over e to the 2 and then some humongous number there, what do you have? You have a humongous number in the bottom, so it goes to 0, right? That's the idea. Constant over infinity is going to tend towards 0. So what you're going to have is you're going to have negative 1/2 times 0, and then the limit of a constant is itself. So you're going to have negative 1/2 times negative 1. That's going to be 1/2, okay? So we have a definitive area under that curve, even though we're taking a limit from 0 to infinity, okay? That's pretty bizarre, but that's the way it works out, okay? Does that make sense? Okay? So yeah, about half of the problem is doing an integral. The other half is doing a limit. That's the idea. Okay, any questions? Okay. All right, let's take a look at this next one here. And with this next example here, I went ahead and just put this in the calculator. It just kind of give an idea what's going on this, okay? And I think I did let me grab my notes here because I think there was a little calculation I wanted to show on here. So I just don't have to get my calculator out. Yeah, I was mainly just kind of show this. So like 4 over pi is in here somewhere. So I mean, the key thing is you have a point. You're looking at 4 over pi. And then I'm not going to do the function value but if you did f of 4 over pi, you would have what that point is then. So you're just kind of starting here, and then you're going to do an integral of that. You're going to find the area under the curve like that. Okay, so what's unbounded is this, okay? If you look from 4 pi to some point on there, the thing is that I want you to understand, you don't look all the way out there. It's just from 4 pi to some point there, that area is bounded. It's bounded by the x-axis, this, and the curve itself. So just kind of pick a point, and you can draw a circle around that, so that's bounded. That's what I mean by that, okay? So what we're going to do is kind of get this one set up the same way. It's an improper integral. So the first thing you want to do is just replace that infinity with b or some letter. So let's write this as the integral going from 4 over pi to b. Then we're going to have 1 over x squared, secant squared 1 over x, okay, times dx like that. Okay, so we're going to do that. And then what we're going to do is we're going to do the limit as b approaches infinity. So that's how you set up the improper integral. Okay, does that make sense? Okay, yeah. That's fine. That's fine. You could go to the kind of the side and just devote your time to the integral and the limit later. If you want to write your stepwise, that's fine. Okay, just don't forget to do the limit. The reason I do this, sometimes I get my integral and say yay, and then I forget that what I'm even doing. Okay. All right. So let's go through. Now we're going to focus totally on the integral here. So, and we can kind of get that done. Okay. Secant squared. When I see a secant squared, what's the antiderivative of secant squared? A tangent. We know the derivative of the tangent secant squared. So this looks like a good U-substitution problem. So what I'm going to do is let's work with u being 1 over x, because that derivative is going to get you something close to 1 over x squared. Okay, so let's just kind of do this in here. Let's use u is equal to 1 over x. You could rewrite that as u equals x to the negative 1. Okay, so that's going to be my u. Now let's do du and see where we are with this. So du is going to be negative 1 x to the negative 2. So that's du equals negative 1 over x squared. So we're pretty close. We got that x squared there, but we're off by a negative. So you can just write this as negative du equals 1 over x squared. Okay, so that means in my substitution, and I need to have my dx on there, shame on me. Okay, like that. So that means that 1 over x squared dx, that piece right there is going to be replaced with negative du. Okay, and then we're going to do our limits also. You might as well just change your limits of integration as well. So when I get this integral put together, I'll do my limits here in a minute. You're going to have secant squared of u, and then you're going to have 1/2 dx. That's going to be negative du. So I'm going to put the du there, then I'm going to put the negative there. Okay, does that look good? Okay, we've now kind of officially done tons of U-substitution this semester, so everything's accounted for now. Okay, now when we do the limits, okay, it's good to just change them now. So we have 4 over pi. If you change that, what's your U-substitution? It's 1 over 4 over pi. So that's going to be pi over 4, right? Because you're just doing a reciprocal. Okay, so that limit of integration there is just going to change into pi over 4. Okay, then you got your upper limit of integration, which is b. So you're going to do just 1 over b. So you're going to do that also. Okay, now that's step 1 is to do that. And then you're going to end up doing the limit of that integral once you do that then. Yes. Say that again. No, you need to wait and do that. I think what you're thinking is the limit. You don't want to do the limit until you're done with the integral. Don't skip any steps there. I mean, get your integral done, and then the limit is the very last thing that you want to do, okay? Because, see, we don't know how that's going to turn out yet, okay? Try to see what your point is on that. Okay, so anyway, we're going to have this. Let's just go ahead and work the integral out, and then we'll do the limit at the end like this. Okay, so what's the antiderivative of secant squared? That's tangent of u, and then we're going to be evaluating that from pi over 4 to 1 over b, like that. Okay, that's going to be, yep. You okay? Oh, okay, yeah, okay. The negative came from the U-Substitution. So we have negative, and then we're going to have tangent of 1 over b, and then we're going to have minus tangent of pi over 4, like that. Okay, let's go ahead and get this done before we do the limit. So that's going to give us, and you can just leave it in that form, actually. It'd be just as well to leave it in that form, or you could distribute the negative through at your call. Okay, so, well, let's actually take it through. Why not? Okay, so we got negative tangent 1 over b plus tangent pi over 4. Okay, now what we're ready to do, see, is now we're ready to do the limit. Now you have to dig into your trig background on this, okay? So you're going to do the limit now as b approaches infinity of negative tangent of 1 over b plus tangent of pi over 4. Now, there's one other thing, well, I'll do that in the next step here. We're going to do that. So there's two things that you have to consider on this, okay? First of all, you got to dig into that trig background a little bit, okay? Pi over 4, what is that point on the unit circle? Square root of 2 over 2, square root of 2 over 2. That's the reason why your trig teacher, a lot of you, I was your trig teacher, made you memorize that unit circle. Because it just keeps popping up, doesn't it? It's like God, okay? You have to refer to God a lot of times in here. So what's the tangent there? It's 1. It's y over x, right? Okay? So that's going to be 1. So you're really going to have the limit of, as b goes to infinity, of negative tangent of 1 over b plus, and then the tangent of pi over 4, we said that that's equal to 1. So you could go ahead and evaluate that and get that. Okay? Now we're finally ready to do the limit. Does that make sense so far? Okay. Tangent of pi over 4 is y over x, so that's 1. Now we're ready to do our limit. Okay? Now you can kind of do a lot of this in your head. Just kind of consider this piece right here. Just consider that you're going to be making b go to infinity. Well, what you're going to really have is you're going to have this. You're going to have negative tangent of 1 over infinity. Well, what's 1 over infinity going to? Let's go into 0. So that's heading towards negative tangent of 0, which you can do on a unit circle. You can figure out what the tangent of 0 is then. So you're going to have, basically you're just going to end up having negative tangent of 0 plus 1. Okay? Now if you go to your unit circle, at 0 radians, you have the point 1, 0. So what's the tangent of 0? 0, because it's y over x. So you would have negative 0 plus 1. So that means the answer to this problem then is going to be equal to 1. Believe it or not, that's the area under the curve. Okay? Now see this last piece right here. You can kind of begin to do these limits in your head. I mean, you just kind of look at, okay, that's going to go to 0, right? So tangent of 0 is 0. So that last step, most of the time, you're going to reason that out in your head. And let's see, you were asking up here in the front, I forget your name, but you were saying, let's go ahead and make 1 over b 0 now. If you did that, you might not ever have that tangent there. So you got to wait till the end until you let that go to infinity. Okay, the limit's the last thing you do. Okay, any questions on that? Okay, good stuff, isn't it? I think it is. I think it's fascinating. Of course, I think everything on this stuff is fascinating. I think calculus is just fascinating. All right, let's do one more illustration here. I will take a break after example 3, okay? Okay, I didn't put a graph on this because the variables are in terms of y. And it doesn't matter, you don't even have to look at graphs on any of these things. So let's just not even pay attention to the graph. Okay, step 1 on this one is you're going to change this integral to 2 to b. You have unbounded limits of integration. And then we have dy over y ln y like that. And yeah, you're going to do the limit as b approaches infinity. So that's what your goal is, to do that. So step 1 is we need to just really focus on this integral over here then, okay? All right, so let's see. This looks like U-substitution, okay? What I see is an ln y. Okay, if that was u, then what would be du? If u is ln y, what's du? 1 over y, which is there, right? You have the 1 over y there. So that's how you're going to do the U-substitution. So let's focus on that first of all. So let's let u be ln y. Then we know that du is 1 over y times dy. So let's say it's going to be a real straightforward substitution. So you got, there's your u, okay, right there, and then this is your dy over y, that's going to be your du. So that's a real simple one. Okay, so our integral is going to be, and we're not going to worry about the limit, we're just going to do the integral from I need to change my limits of integration too. It's a good idea to just do that. Well, let's go ahead and get this set up. So what we have is du over u, like that. And then your limits of integration. Okay, you can do that now. You're just going to do ln of y. So the b is going to become ln of b. Just leave it alone. And then the 2 is going to become ln2 like that. Okay, so we're going to change those limits of integration to ln2 and lnb like that. Okay, so then we're ready to go with that integral to get that done. Okay, what's the antiderivative of 1 over u du? ln of u. Okay, and then we're going to evaluate that from ln2 to lnb like that. Okay, and we're going to kind of have logarithms within logarithms, but that's okay. So when we go ahead and evaluate this then, we're going to have ln of lnb like that. Okay, and then we're going to have minus ln of ln2 like this. Okay, and then what we can do on that is we can go ahead and do the limit now if we want to, because you're going to let b go to infinity like this. And what's going to happen on this one's kind of a weird thing. Now, I think what you could do on this one too, if you go through now and do your limit, just kind of as your second step, you do the limit as b approaches infinity. Let me just show you what happens. You don't need to do anything with those ln expressions. So we have ln of lnb, then minus ln of ln2, like this. Now let's just think about what's going to happen if b becomes an infinitely big number. Okay? Well, what's going to happen is if you do the ln of infinity, it just gets bigger and bigger and bigger and bigger. Okay? An ln graph, if you don't remember the ln graph, I'll just do a real quick graph on this just to illustrate this. If I do y equals ln of x, okay, I'll just do this in standard window. It's going to increase without bound. Now it looks like there might be a horizontal asymptote. There isn't. I need to take that off. That was from some other class, obviously. Okay, so that thing gets bigger and bigger infinitely. Okay, so if you're doing the ln of b, it just gets bigger and bigger and bigger forever. Okay, so this whole thing right here, that whole thing right there would just be going to infinity, right? Okay, now this is a constant, right? If you do a limit of a constant, what do you get? You just get a constant. I mean, you don't have to put this in here. The decision has been made that that's infinitely big, right? Okay, So when you did that area of the curve, it became infinite. Okay, so what we say is, if that happens, is we say that this diverges. Okay, and I'll explain just a little bit about what that is. All of the improper integrals we've done so far have converged. That means they went to a definitive answer. That's what convergence means. Divergence means it did not go to a definitive answer. It went to infinity, so that means that area under that curve on this did not converge to some precise amount. That goes to infinity. You'll find that a little bit every now and then on these problems. You're going to find that not all improper integrals are going to converge. Some of them are going to diverge. Okay, that will happen. Okay, does that make any sense? Okay, all right. And the idea on this one was that thing just became infinite. There was no boundary there. So that's the idea. Okay. All right. So let's pause here and do a 10-minute break.